Hello. Good morning, everyone. My name is Nilesh Yadav. Today I'll be speaking on the topic attributes of graphic primitives. The primitives are the simply geometric functions that are used to generate various computer graphics required by the user. Some most basic output primitives are point position pixel and a straight line, curve, polygon, etc. In this video, we will go over the basic understandings of the color and grayscale, line attributes, curve attributes, fill attributes, character attributes, and finally we will have a look at anti-aliasing. Starting off with attributes, as said earlier, the basic primitives are pixels, lines, curves, and polygons. Each primitive is associated with a parameter which tells us how the primitive is going to be displayed. One such parameter is color. Color information can be stored within frame buffers in two different mechanisms, like either we can make use of RGB color codes directly saved into frame, which can lead to bigger frame sizes, or putting into tables and with the help of pixel location and corresponding color. Here we can see how the 8-bit memory is allocated to each pixel, thus giving us 256 colors. So 1, 2, 8. So these 8 bits will give you 256 colors. So this is a 256 color lookup table. Here the previous concept is taken a step further, and now each pixel has 3 different groups of 8-bit memory, each red, blue, green. This thus enables more than 256 colors. Apparently it gives us a million of colors. Photoshop uses this picker to get the yellow color. Color lookup tables, also known as the video lookup tables, helps us in reducing the size of frame buffers. They are responsible for transformation of pixel memory into physical visible colors. As the color parameter is associated with all primitives, it gets easier to experiment without changing other attributes. Here we can see how the pixel 196 on the screen is associated with the 256 entry color table. The entry has the value of 2081, which when converted to hexadecimal format goes to 0x0821, which in return controls the intensity of red, green, and blue guns on monitor screen. Gray shade can be obtained when the red, green, blue is taken into equal amount. It can be altered to a darker or lighter shade depending on the value for the color components. To observe the display and these color changes we talked about previously, we make use of our eyes. Let's get some technical insights of our eyes with respect to computer graphics. Human eye is capable of capturing a range of 24 f-stops. However, when the pupil opening is unchanged, it can capture only 0 to 14 f-stops, which is as good as that of a certain DSLR cameras. Now, moving on to our main focus topics of primitives and their line attributes. Let's start with the first primitive, line. A line is composed of series of pixels or dots in a straight manner. It has 3 basic attributes associated with it, like color, width, and style. So as far as we have seen the color attribute of all the components, now we will be moving on to the thickness or the width of the line. Displaying thick lines can be done using any of the mechanism like plotting additional pixels along adjacent parallel line paths, using vertical spans of pixels in each column along the line, using horizontal spans of pixels to the right and left of the line path, or it can be done by fill rectangle or paint brush patterns. Here we can observe the thick line with the help of horizontal and vertical columns. So the image A shows you the horizontal, like the blue ones are the actual line path, whereas to thicken it, we can see horizontally placed pixels. In the B, we can see vertically placed pixels. You can also observe that these column techniques have created the endpoints for the lines which are not matching with the slope. This can be solved with the help of line caps. Now, there are three types of line caps: butt caps, round caps, and projecting square caps. Here we can see those three types. Butt caps, it has a square end that are perpendicular to the line path. That means 90 degree to this line. Let me just see if I can draw. So this perpendicular to the line path. If the slope of the line is m, then the slope of square ends is -1 by m. Round caps, adding filled a semicircle to each round cap. Like here we can see the squares. All we have to do is just add a semicircle to it and it gets done to the round cap. Projecting square caps, simply extend the line and add butt caps that are positioned to one half of the line width beyond the specified endpoints. So here you can see the butt caps. All you have to do is just increase the width and set it. So this will happen as square caps. Now, when we consider multiple lines, let's say to form a shape, in this condition, horizontal and vertical columns will generate pixel gaps between line segments due to different slope of line segments. The size of gaps depends on the slope of line segments. To remove these gaps, we need to perform extra processing at the endpoints. These processing can be named as mitre join, round join, or bevel join. Diagram A shows you mitre join, which is extending outer boundaries of each of two line segments until they meet the meeting point. Round join, capping the connection between segments into circular boundary with diameter equal to line width, like this. Here you have capped it as a circular part. Bevel join, displaying the line segments with butt caps and filling in the triangular gap where the segments meet. Butt cap, and then join this. Moving on to pen and brush options to draw thick lines. This option includes attributes like shape, size, and pattern of the pen or brush. Here we can see the pen or the brush starts from here. However, to make it thick, these pixels are also considered, and as the line path goes, these pixels continue to go with it. Here we can see it. Till now we have seen the color and width attribute of line. Now we will see more about style. Line can be styled in three ways, as solid, dashed, or dotted. When style is other than solid, we alter the line drawing algorithms by setting the length and spacing between the solid sections of line path. Here we can see an example of pixel mask which is generated for line with solid length of 5 pixels and spacing of 3 pixels. Curve attributes. Curves are formed using the lines. When the line is not in a straight manner, it can be called as curve. As it is derived from line, it has similar attributes as color, width, and styles. Thick curves can be obtained either by horizontal and vertical spans or filling the area between the two parallel curves, whose separation is equal to the desired width. Here we can see the examples. These are horizontal and vertical spans, which makes the curve thick. Here we can see a curve and then a parallel curve of the desired width. Styling is similar to that of line with the use of pixel mask, whereas we can see an example over here which gives you an arc of 3 pixels, then 2 spacings, 3 pixels, 2 spacings. Heading to our next topic, fill area and its attributes. There are 3 basic polygon fill styles: hollow, solid, and patterned. Hollow, as the name suggests, it is not filled and just has the borders. Solid is filled till the borders, and pattern fills the polygon with a particular pattern depending on the mask or inside outward painting of pixels till the boundaries. We can also make combination of pattern and solid by either of the options shown here, like pattern, solid, and we will get the resulting options. So when we do AND, this is 1, this is 1, we'll get 1. 0, 1 will give you 0. Similarly for OR, 1, 1 will give you 1. 0, 1 will give you 1. 1, 0 will give you 1. And similarly. Scan line polygon fill. So when we use scan line fill, it is performed by the intersections of the scan lines with the polygon lines. Here we can see 10 to 14 and 18 to 24 are intersecting on the scan lines. Then these are considered and colored. Here we can see the scanline polygon fill algorithm, where the scanline y prime, that is this, has 2 intersections or even number of edges, that is edge 1 and edge 2. However, while scanline y just has 1. Okay. One of the methods for implementing the adjustment of the vertex intersection count is to shorten some polygon edges to split those vertices that should be counted as one intersection. Here we see, here we see 2 intersections, 1 intersection. So when such a thing happens, we need to adjust the vertex intersection count. So here we can see the intersection count for scanline Y is 2, then it is decremented to 1 by 1 unit in line A. Similarly, it happens in line B. Now for the scanline polygon fill algorithm. So this is the algorithm which tells you everything of how to be done and what to be done. So store the polygon boundary in a sorted edge table that contains all the information necessary to process the scan lines. Either in a clockwise or counterclockwise order, use a bucket sort to store the edges, sorted on the smallest y value of each edge in the correct scanline position. Shorten certain edges to resolve vertex intersection question, just how we seen in the previous slide. Each entry in the table for a particular scan line contains the maximum y value, the x-intercept value, and the inverse slope of the edge. Process the scan line from the bottom of the polygon to its top, producing an active edge list for each scan line crossing the polygon boundaries. The active edge list for a scan line contains all edges crossed by that scan line, with the iterative coherence calculation used to obtain the edge intersections. This is how the table from step 2 of the scan fill algorithm looks like. Here we can see a line YC just has one vertex or one entry. That is because it has just one vertex intersection. This one, C to B. Okay. Similarly, there are two entries for YD and YA as there are two intersections. We can also observe that DC is shortened by 1 unit and renamed to DC prime. Scanline fill methods. Let's talk about how these polygons are filled. We can make use of boundary fill algorithm where the boundary of the region is specified in a single color and we can fill the color from a point, pixel by pixel till we reach the boundary. It checks for the neighboring pixel. If it's not the boundary, then it changes to fill color. This can be done in two ways, 4 connected or 8 connected. Here we can see the methods 4 connected and 8 connected. The difference between 4 connected and 8 connected is the diagonal pixels. As the 8 connected takes consideration of diagonal pixels, it is much more correct than the 4 connected. This is the code where we can see the implementation of boundary fill for 4 connected. And if we need to change this boundary fill 4 to boundary fill 8 connected, all we need to do is include additional statements where the diagonal pixels are considered. Here we can see the stack implementation of the 4 connected boundary fill. Diagram A. The area is divided into two parts, 1 and 2, and is stored in stack 1 and 2, this being the entry pixel. Diagram B. The area 2 is filled and popped out of the stack, and area 3 is pushed into the stack. Diagram C. Area 3 is filled and popped out, while the new areas 4, 5 and 6 are pushed into the stack. Diagram D. Area 6 is popped out of the stack and filled, as stack is last in, first out. Wireframe methods. These can be used to create a three-dimensional diagram from a two-dimensional flat diagram of a polygon. Character attributes. Character is associated with various attributes depending on the appearance of the character, which depends on the font, size, color, and orientation. Here we can see the character body, then the gap between top and the cap, the character height, and the gap between base and bottom. For certain characters, there is a term called as kern for the curves, like F and J as shown in the figure. Then this is related to the height of the characters, width, and the spacing between two characters. The direction of a character, you can see the down string, and the text path direction, right string. See the difference between A and B. This is the text path, while this is the direction of character up vector. Anti-aliasing. We know that the computer screen is made of pixels and each pixel is square in shape. Thus, when we draw curves, we see a stair-step effect due to which the image does not look smooth. To make the image smooth, we use anti-aliasing techniques, which samples the data around the curves and fill it to form a smooth image. We can also have a look at this video which shows you how actually the anti-aliasing works. So as we have seen in the video, the anti-aliasing techniques can be done with the help of improving the resolution or increasing the samples. Another method of anti-aliasing is area sampling, where we calculate the pixel intensity from the areas of overlap with objects to be displayed. Filtering techniques, which will give you more accurate method for anti-aliasing lines. There are three different filters like box filter, cone filter, and Gaussian filter. Here we can see in both the images how anti-aliasing helps in smoothing the image. You can observe here the stair step effect. And here the effect is lowered. Similarly, if you see here, you can see edges on the curve. However, after anti-aliasing using the technique of super sampling, the curve is smoother. So that's it from my side about the primitives of computer graphics. Thank you everyone.